So, in the previous video, we gave this long list of criteria, we proved this long list of criteria for compactness of a metric space. And as I said, a subset of a metric space is compact if it's compact with induced metric or induced topology, if you like. So how does that actually translate into actionable concepts and things that we can use, right? So suppose that K is a subset of X, which is complete, right? So X is our metric space, K is a subset. Well, we have this definition of compactness for a subset, which we saw before, right? That anytime K is covered by a union of open sets in X, there's a finite collection of those open sets that still covers K. Now, the second criterion is a bit more subtle. Remember that a metric space is compact if and only if it's complete and totally bounded. Here I'm saying closed because we know that if you have a subset of a complete metric space, then the subset is a complete metric space with induced metric if and only if it's a closed subspace of X. Therefore, when I say K closed, that implies, or is actually equivalent to saying that K as a metric space itself with induced metric is complete. And totally bounded doesn't change, right? Doesn't only means that it has finite epsilon covering numbers, meaning I can cover K by a finite number of balls of radius epsilon for any epsilon. Or the largest epsilon packing contained in K is finite for any K, for any epsilon, sorry. Okay, so this criterion number 2. And number 3 is the subsequences criterion, right? So if a metric space is compact, well, it's if and only if, right? Any sequence in a metric space has a subsequence that converges to an element of this metric space, right? So actually, when I say converges to an element of that metric space, that doesn't even need to be said, right? So that goes without saying, so to speak, because in a metric space, there's no, in principle, there's no outside. There's no chance that something would converge to an element outside. Here, we have to be more careful. When we say that a subsequence in K converges, in principle, it could converge to something outside of K. But here we require to be careful that any sequence in K has a subsequence that converges to an element of K. So these are the conditions that we have for a subset of a complete metric space to be compact. And now we're going to apply them to RD. And in RD, we have a very classical statement that gives us a necessary and sufficient condition for a subset to be compact. So a subset of RD is compact if and only if it is closed and bounded. So this is different in that instead of asking the case be totally bounded, I'm simply asking that it's bounded. No, totally, right? So, and what's behind this is actually that a subset of RD is bounded if and only if it's totally bounded. How do we prove this? Well, there are different ways, right? So let me first give an argument that gives this directly. Right, so it's clear that if I know the second statement, I know the first, right? So that bounded is the same as totally bounded for subsets of RD, then I have this definition. But let me first prove something that bypasses the statement. Suppose I have a subset K of RD that's compact, then, well, it has to be closed by 2. It has to be totally bounded. But if it's totally bounded, then K is contained in a union of balls, so of radius, say, 1. And then you can see that for all X and K, the norm of X, or let's say the Euclidean norm of X, is less than, well, K is contained in here, right? So I can just say, okay, norm of X squared, Euclidean norm of X is less than the norm of X minus Xi, 2, plus the norm of Xi, for any I, but I know there is an I such that X belongs to this ball, so there is an I such that is less than 1. So here this is less than 1 plus the max of the norms of the xi's. And since I have a finite set here, this maximum is finite, and what I've shown is an absolute bound, as an upper bound that's finite for the norm of any element in K, therefore K is bounded. This argument actually works in any metric space if you replace these by distances to some fixed element. So I don't know, call this element X. You still have something like this with the triangle inequality and distance X sub I. This is O. Of course, if we're in a normed space, then the natural kind of fixed element to compare guys to is the origin, but we don't need the origin. We can do this over any metric space. So what I'm saying is that a totally bounded subset of a metric space or a totally bounded metric space has to be bounded, has finite diameter. Take any point, there's an absolute upper bound for the distances from this point to any x. So okay, bounded always implies totally bounded. What about the converse statement? As I said, there are kind of two different arguments, and one of them is specific to our G. Well, it kind of uses a previous exercise where we showed that if you have a bounded subset of Rd, any sequence has a convergent subsequence. Now, that's not enough to say that any bounded subset is compact, and we know that not all bounded subsets are compact, right? So what gives? So what happens is this. So suppose K is closed and bounded. Then every sequence in K has a convergent subsequence. And because K is closed, the limit of the subsequence has to be in K. So if K is closed and bounded, this criterion 3 is satisfied. But then there's a more direct proof that in Rd, or more geometrical perhaps, that a subset of Rd is bounded if and only if totally bounded. We've already shown that totally bounded implies bounded. What about the converse? Well, if a subset of Rd is bounded, that means that, say, max of, I'm just going to use the infinity norm because it's slightly more convenient, or this is actually a soup. This is less than some n, which is finite. But that means that K, all coordinates of points in K are bounded by n, and therefore K is contained in this Cartesian product. Right, we're in Rd. So here I'm taking the interval of the line minus n to n, and I'm taking the Cartesian product of this interval with itself and d times, and K is contained in here. And now if I want to show that I can cover K by a finite number of balls of radius epsilon, I just needed to cover this guy. But that's easy. Basically, I'm gonna sketch the argument here. Here I'm doing it for d equals 2. Basically, you have to take this box from, well, okay, let me add the axis. There's minus n, minus n. You have to subdivide this box into smaller boxes, a finite number of them. Well, and you can say this, so let me divide each one of these intervals into m pieces. So in total, I'm going to have m to the d boxes, right? Because I'm dividing by m, and then dividing by m, then dividing by n, doing that d times. So I have these boxes, and I'm dividing by m into intervals of equal length. So the lengths of these intervals are going to be something like, well, the length of one guy is to n, and divided by m, and maybe I have to round up a little bit just to, I have to make these lengths here less than the ceiling of this, right? I have to round this to the nearest, yeah, I have to make this a little bit larger. Sorry, so this is not what I want. I want to divide into pieces of size like this. Yeah, you're going to have a little bit of an error because if you divide exactly into m pieces, maybe there will be a piece that's a little bit larger, but that's not a problem. Oh, no, sorry. Never mind. You can divide into m pieces, right? I just take intervals of length 1 over m here, and I put m of them in each coordinate. And these boxes have this length. So now if you take the ball center at these points with, right, so each box is contained in the ball around its center of radius, okay, then you have to check that in a box like this, the largest possible length of an interval in here is something like, okay, in the infinity norm, it would be 2n over m. And since if you want to use the 2 norm, you have something like square root of d to n over m. So each box contains a small balls of very small radius. There are finitely many boxes, therefore you need finitely many balls. And you want to cover it by balls of radius epsilon, right? So you just have to take m large enough, so this is less than epsilon. If you have that, you're done. So what I'm saying is that basically you can prove that any bounded subset of Rd is totally bounded by arguing first that the subset is contained in a box like this, and then proving that the box is totally bounded, that it can be covered by balls of radius epsilon for any epsilon, and you can just use the splitting procedure to prove it. Okay, so just give you two proofs of this very classical theorem. Of course, there's a reason why we asked that that we have Rd over here in the space to say continuous functions, which you know is a Banach space, so it's a well-behaved vector space with its norm. So I mean it's complete and everything. Then okay, look, one thing that this implies is that all closed balls are compact, right? In particular, the unit ball around 0 is compact. This is not the case in, say, the space of continuous functions that we always look at as kind of our next simplest example. The unit ball around 0 is not compact. And that's because, well, it's surely closed, so it cannot be totally bounded, right? And how do you prove that? Well, I'm just going to build, you remember this notion of packing, right? So you remember that we proved that when a metric space is not totally bounded, it must contain an infinite packing, an infinite set of elements that are within distance, say, the distance between distinct elements are at least, say, epsilon. In this case, they're going to be at least 1. And how do you build these functions? So one way is this. So you divide the interval into pieces like 1, 1/2, 1/3, 1/4, and so on. Now the functions you're going to build, the packing you're going to build is going to be like this. So function number 1 has a stand shape, maximum equal to 1, and it's 0 outside. Function number 2 is going to be similar. It's going to be a kind of a tint. It's a S tall as the other one, but with a disjoint support. And you keep doing that forever. So function number 3 is going to be like this. And if you look at this sequence of functions, it's explicitly written down in the notes. So the sequence of functions contained in this ball and all functions are within distance 1 from another. And you can see this, for instance, for the first two functions, or the second and the third, that they both reach maximum value equal to 1, but they're all the regions where they're non-zero do not overlap, right? So this one is non-zero only in this open interval here. This one is non-zero only in this open interval. This other open interval. So when one of them is 1, the other is 0, and vice versa. So you can show that the maximum really is exactly 1. And now you have an infinite packing, right? So because the sequence, as I said, keeps going forever, so you have another element like this, you have an even tighter tent. So the unit ball contains an infinite packing. Well, I mean, if you want a packing, you want an epsilon packing, you need all distances to be greater than epsilon. So here you can say all distances are greater than 1/2, say, and you have an infinite 1/2 packing. Therefore, this unit ball is not totally bounded. And it's going to be a non-trivial result called the Arzelà-Ascoli theorem, Arzelà-Ascoli, I guess, that describes what the compact subsets of the space look like. Okay, so now you understand why Heine-Borel is restricted in application to RD. You cannot just have any metric space or a vector space here. It turns out that there is a lemma by Ries that's very famous that says that if you have a Banach space where the unit ball is compact, that means that your space is finite dimensional, meaning that there's a finite basis for it. I'm not going to get into that. That's not a subject for this class, but it's good to know that somehow dimension is tied in with this compactness property for the unit ball. Okay, but now that we have Heine-Borel, we're going to do a very simple and very classical application of it. I had promised to prove the spectral theorem using this. We're going to leave that for later, actually. But because we can do it more easily once we learn a few things about Lagrange multipliers. But I want to prove the statement that all norms over Rd are equivalent. I'm going to prove that they're all equivalent to the 2 norm, to the Euclidean norm, but then you can, from that, prove that all norms, any 2 norms are equivalent. I'm going to remind you of what that means, and so theorem. Any norm over Rd equivalent to the 2 norm. And what does that mean? Well, 2 norms are equivalent if they give rise to the same topology. But we saw earlier that there's equivalent description, or pun intended perhaps. There's a description that is this. So there's another way to say it, which is to say that there exist positive constants such that for all elements of Rd, C norm, well, okay, given another norm, right? So for all norm double bar, there exist constants such that the Euclidean norm is bounded above and below by, well, below by little c times norm of x, double bar norm of x, above by capital C, double bar norm of x. Okay, we know this sort of thing for, say, when these norms are the LP norms. We just did calculations by hand. We know, for instance, that if double bar is the infinity norm, then you can take little c to be 1, capital C to be square root of d. We know constants for all the other LP norms, or at least we should know. But the point is that such constants do exist for any norm you choose. Again, this is something very specific to finite dimensions. We had, at some point, we had this L1 norm over the space of continuous functions, which is a norm defined by the integral of the absolute value. That was a norm, but we know that with that norm, the space of continuous functions is not complete, and we can find sequences that converge to 0 also in that norm that do not converge to 0 according to the standard infinity norm. Therefore, that's an example of a vector space where there are 2 norms that are non-equivalent. And but in Rd, in finite dimensions, we don't have to worry about such things. And okay, how do we prove this statement? First thing that I'm going to need is that with the usual topology, this space of vectors with the set of vectors in norm 1 unit sphere that we all used to is compact. Okay? So how do we know this? Well, it's closed because, say, it's the boundary of the unit ball, if you like. And boundaries are always closed because, remember that the boundary is the intersection of the closure of a set with the closure of its complement. Closures are closed, intersections of closed are closed, so the boundary is closed. And it's certainly bounded, right? Because all norms here, all vectors here have a norm less than or equal to 1. They actually have norm equal to 1, but it's bounded. So if it's closed and bounded by Heine-Borel that we just proved, it's compact. And now I'm going to define a continuous function, which, unsurprisingly, is the function that maps x to this double bar norm of x. And if I can prove that this function is continuous, then I'm going to be able to compute its infinite sup, and the inf is going to be little c, the sup is going to be capital C. Okay, I'm going to prove that actually this function is Lipschitz, and I'm going to do it, well, with a constant that I still don't know what it is. G of x minus g of x prime. This is equal to norm of x minus norm of x prime. By the properties of norms, we have subadditivity, right? So we know that this is at most norm of x minus x prime. And now I'm going to use the fact that I'm infinite, that I have a canonical basis for D, because I know I can write this difference here, right? So if I want to write a vector, I can write it by looking at the coordinates multiplied by the canonical basis vectors. And now I'm just going to apply subadditivity of the norm. So I'm using strongly the fact that double bar gives me a norm, of course, right? I used it here. Now I'm going to use it again. Now here I have, okay, I have at most m is the maximum of these guys, times the L1 norm. You can see I have the L1 norm here, right? So, but the L1 norm we know is bounded by square root of d times the L2 norm. And let's see what we did. So what we did here, hopefully you can read this, or maybe not. So let me move this over here. So all I've said is that I have some xi minus x double I norm of ei. So these guys here are all less than a constant called m, which is just the largest of these norms, the maximum of these guys, right? I have finitely many canonical basis vectors. Each one of them has a norm. I take m to be the maximal norm. And then if I replace this by m, I'm left with m times the L1 norm of the difference, which is less than m times square root of d times the L2 norm of the difference. So with all that, I've proven that G as a function over the sphere is m times square root of d Lipschitz function with respect to the standard Euclidean norm. Therefore, it's a continuous function with the standard topology over Rd, which is the topology under which I know that the set is compact, right? So, okay, now I know I have a continuous function here. Okay, so I'm just gonna, I got Lipschitz, all I needed was continuous, so, but that's good. This is continuous. So I'm gonna define C to be the infimum of G of x for x in the sphere, capital C to be the sup, I claim, first of all, that C has to be bigger than 0. And why is that? Because G is a continuous function, therefore it achieves its infimum, right? It achieves its infimum at a certain vector that I'm going to call x minus. And this vector belongs to the sphere. Therefore, this vector is not 0. And we know that the norm of a non-zero vector is non-zero. Therefore, this is a norm, right? So I don't know which norm this is, but it surely is a norm. So this cannot, if x minus is not 0, this cannot be 0. So C is greater than 0. Capital C is also greater than 0 because this guy is at least as big as this one. And the important thing for us is that capital C is bounded, is finite, because again, this is a continuous function of a compact set, right? So we are using twice the fact that the sphere is compact and G is continuous. But now we're done. And how is that? So I claim that this inequality here holds, right? So, and now look at this. So I want to prove this now. If x has norm 0, if x is equal to 0, then this is clearly true because I have 3 zeros here. And 0 is less than or equal to 0, this is less than or equal to 0. What if x is non-zero? Then I can divide by the Euclidean norm here. I can just say, okay, for all x in Rd not 0, I have that x divided by the Euclidean norm of x is in the sphere. And since this guy is in the sphere, g of it is less than capital C and greater than small c. But what is this, right? So this is just the norm of this vector, and the norm is positive homogeneous, right? So this constant goes outside. Now, okay, now I don't have a vector in the sphere. I'm just saying, okay, norm. If I take x and normalize it by the Euclidean norm and have a vector on the sphere, therefore it's double bar norm between little c and capital C. But this is basically there's an equality, right? So have I done anything? No, that's a, yeah, okay, so I lied a little bit, right? So these constants are not the same constants on top. I proved this. But it's easy to see that once I have this statement, I have the other one. For instance, I'm saying, okay, the double bar norm is upper bounded by this constant c tilde times the Euclidean norm. So I can take this guy to be 1 over c tilde, the capital C tilde. And over here I have that the 2 norm multiplied by c, small c tilde, is less than double bar norm, so I can take this guy to be 1 over little c tilde. And now I'm done. And again, okay, I just need to prove this for x different than 0. And yeah, so that's what I have. So I guess I could have made my life a little bit easier just by saying I want to prove a statement with the 2 norm here, 2 norm there, and double bar norm here in the middle. But these things are always equivalent. So if you have constants on two sides, you can flip between one norm and the other just by adjusting the constants. And this is what we did here. So now, okay, just to recap, we given criteria for a subset of any metric space to be complete, and particularly suffices for a subset of any complete metric space to be compact, and particularly it suffices for a K to be closed and totally bounded. We observed that totally bounded for a subset of Rd is the same thing as bounded. And now we know that the Heine-Borel theorem, which says that closed and bounded subsets of Rd are compact, and compact subsets of Rd are closed and bounded. And now I proved this equivalence of norms, meaning that basically all norms of Rd give you the same topology, gives you the same notion of convergence, and there is even this quantitative relationship between the two norms. You can bound one norm above and below by the other up to constant factors. Of course, these constants depend on the norm, right? Okay, so that's what we wanted to do right now for Rd. The next thing we're going to do is to look at spaces of continuous functions, and there are going to be two things we're going to do. First of all, we're going to greatly extend the space C01R. I'm going to allow any compact domain, any complete counter domain. And then I'm going to prove some properties of that space. And finally, we're going to prove a theorem, which I already mentioned, Ascoli, that describes the compact subsets of the space of continuous functions. And with that, I finished. Thank you very much.